experiment. We found out that the biophysics colloquium, so this is an interdisciplinary colloquium, meets at the same time as the physics colloquium, which is really, really unfortunate. So we are trying to set up a few joint colloquia throughout the year, and so next week's going to be the first one. So the first one speaker is Najib from Jacak Farms, who's going to probably try shaking the brain imaging. So that should be very interesting. Today's speaker is Barbara Jacak. So Barbara is one of our newest faculty members. She did her undergraduate degree here at Berkeley, and she did her research as an undergraduate with the legendary Glenn Seaborg, which is pretty impressive. She went on to graduate school at Michigan State University, where she studied nuclear physics at the cyclotron facility. And from there, she became a prestigious Oppenheimer Fellow at Los Alamos Laboratories. So she went there for the fellowships, and then she stayed on there as a staff scientist for just about a decade before she moved to the physics faculty at Stony Brook. And we were fortunate enough to have Barbara join us last year, and she is a joint physics faculty and the director of the nuclear sciences division at LBL. She's also won a very impressive number of awards, including fellowship in the National Academy of Sciences and the American Academy of Arts and Sciences. So please welcome me, and please join me in welcoming Barbara Jacak.
Steve, for that very kind introduction. So I'm delighted to be here to talk to you about strongly coupled QCD matter. It is demonstrably very hot, and I hope in the time scale of the next hour to convince you that it is also very cool. So I'm going to start by talking about what is QCD matter and why you should care about it. And then I'll tell you about some of the discoveries that we've made about quark-gluon plasma. It is extraordinarily opaque, and it flows like a perfect fluid. And in these properties, it's actually got a lot in common with other strongly coupled and strongly correlated matter, and I'll talk a little bit about those commonalities. And then some of the really fun part is to talk about the mysteries. And you might be surprised to hear that one of the big mysteries is what exactly is inside the quark-gluon plasma. I was talking with the students just earlier, and duh, quarks and gluons, but it's actually not that simple. We also don't really know how it transports energy and particles. So after laying that out, I'll tell you a little bit about what's on the agenda to solve those mysteries. So what we do to study quark-gluon plasma is we create the hottest matter on Earth. We heat matter to 10 to the 12th kelvins, which we do in collisions of heavy ions. And the last time in the universe before these colliders started up that such temperatures were seen in nature was a few seconds after the Big Bang. Sorry, a few microseconds after the Big Bang. And so what happens at these temperatures is that the quarks and gluons that make up the neutrons and protons in the atomic nucleus basically dissolve into a plasma of quarks and gluons. So what we're doing is using the accelerators to take a trajectory up here into the quark-gluon plasma, and then we look at it as it cools back down into normal particles that we see in our detector. And the first question is, actually, is there such a thing as quark-gluon plasma? Answer is yes. And the other major question is, so how does it work? And I'll give you some answers. And for some of it, we're still trying to find out. So QCD matter, as those of you who were here for last week's colloquium heard, in QCD, that's the science of the strong interaction. And the strong interaction proceeds by exchange of gluons. A lot is analogous to quantum electrodynamics, except for one really big difference. So unlike the exchange particle of the electromagnetic interaction, which is the photon, gluons are charged. They carry the QCD analog of charge, which we call color. And because they are colored, they can interact among themselves. And that self-interaction means that the number of gluons is not conserved, and the theory is non-abelian. And as far as I can tell, non-abelian is math speak for hard. The reason that it's so hard is because if you want to calculate the interaction between a pair of quarks, you have to calculate the exchange of one gluon, two gluons, three gluons, and so on ad infinitum. That infinite series is what causes the potential to grow as a function of the distance between the two quarks. And as our last week's speaker explained to us, if you solve QCD on the lattice, you have a natural cutoff for the calculation. And that's why we like the lattice so much, because you can calculate QCD in a way that's actually tractable. Now, this large distance behavior causes something rather curious, namely, you never see a free quark in nature, because if you try to separate them, the potential grows. They're actually confined inside hadrons. At very small distances, however, the interaction gets weaker and weaker, and you have asymptotic freedom. And that would tell you that if you could actually take a bag of quarks and gluons and squeeze them so that the average distance is tiny, then the interaction that confines them should get much smaller. Now, that's something that actually can be calculated on the lattice. And the way to think about it conceptually is that if you raise the temperature or the density, you have a lot more colored quarks and gluons around, and those screen this potential. And indeed, here's a calculation on the lattice. The different colors correspond to ever-increasing temperatures of QCD matter. And you can see that when you get to a critical temperature, this large potential is actually completely screened down to zero. And in that case, you should expect a phase transition from confined hadrons to a plasma of quarks and gluons. And using the lattice calculations, again, as Professor Fodor told us last week, you can actually look under the hood and find out that the temperature in which this happens should be about 150 MeV, which is where I got the 10 to the 12th kelvins. Now, how do we experimentally heat to over 150 MeV in temperature? Well, we use colliders. There are two in the world at which we can do these studies. One is the Large Hadron Collider at CERN. The other is the Relativistic Heavy Ion Collider at Brookhaven National Lab. At CERN, we collide lead ions, at Brookhaven gold ions, and sometimes people ask, why are they different? And the answer is just the way the sources were built, whichever ions are the easiest to get out of your source. We collide the heaviest ions we can in order to make a maximum volume of quark-gluon plasma at the highest possible temperature we can reach. And we collide pairs of protons or protons on nuclei for comparison. We think that in those cases, you shouldn't make a large volume of quark-gluon plasma, so that's a control measurement of sorts, and I'll get back to that. So here's an idea of what the experiments look like. These are at Brookhaven. This is the STAR and the Phoenix experiments at RHIC. The right-hand side show you event displays, which tell you something that you probably already figured out, that at those temperatures, if you're going to make enough particles to screen the confining potential, there's got to be a lot of them, and there are. To get an idea of the scale of the experiments, here's a person sitting at the front of STAR working, and this is a man lift in Phoenix. And so they're big. Used to be that Phoenix was my absolutely favorite experiment. That's because I spent 6 years as a spokesperson of Phoenix. But now that I've come to Berkeley, I have a new favorite experiment, and that's the ALICE experiment at the Large Hadron Collider. And here you can get an idea of what an event looks like in ALICE. Pretty exciting high multiplicity. It's interesting that both ATLAS and CMS, which were optimized to do the physics of the Higgs particle rather than study these high multiplicity heavy ion collisions, actually do a bang-up job on these kinds of very, very busy collisions as well. And they also have given us some very key insights. Okay, so now you might be wondering, how do you actually do physics with an event that looks like this? I mean, if I showed you this, you would probably just think, porcupine, sponge, something like that. So what do you actually measure to learn something? Well, the way we study this plasma is actually very similar to what card-carrying electromagnetic plasma physicists do. You can use radiated particles, namely particles that come out of the plasma itself, to tell you about its dynamics and its composition. Plasma physicists would call these internal probes. And then you can use probe particles, things that go through the plasma, and you measure what their interaction with the plasma is like. So what we do, these are it's a calculation actually of two gold nuclei which have just passed through one another. The plasma happens in between. And so we look in between the two beam directions. And ideally, we look at 90 degrees. That's where the sensitivity is maximum to the highest temperature. And so we look at particles as a function of their momentum transverse to the beam direction, or PT. Of course, since the plasma lives for only 10 to the 23 seconds, it's not so easy to send something right through there. And I'll show you how we have a small cheat for that. So this spectrum here is the shape of the transverse momentum spectrum of particles coming out of the plasma. At relatively low momentum, below 1.5 or 2 GeV or so, that's where the radiated or thermal particles from the plasma come out. They come out of the bulk medium and tell us about the properties of that. At high momentum, above 3, 4, 5 GeV or so, that's where we have what we call our external probes. The way we make those is that periodically, when you have a head-on collision of nuclei, once in a while, a pair of quarks or gluons will actually get within a very small distance of each other, so one from each beam, and scatter with a large momentum transfer. That large momentum transfer then causes the quarks or gluons to go off nearly 90 degrees, and they have to make their way out of the plasma before they get to the detector. And so those are our external plasma probes. They're, if you will, self-generated inside the initial stages of the heavy ion collision, and they're very well calculated using perturbation theory and QCD, as I'll show you in a moment. Now, of course, any self-respecting measurement also needs a control, and we do have a nice control, namely photons. Photons don't feel the strong interaction, and so they should get out of the plasma unscathed. And they are produced in gold-gold or lead-lead collisions by QCD Compton scattering. And so their rate is calculable and measurable in proton-proton collisions. Okay, so let's have a look at first at the internal, the thermal probes. What we like to do after we make the quark-gluon plasma is watch and see how it blows up. So here you see a sort of cartoon. This is a pair of nuclei which have collided at some fixed impact parameter. So you have here the region where they overlapped. That's where the plasma should be. And some piece of the two nuclei left over, which are then going along the beam direction at the speed of light. So if you look at this funny interacting region here from the beam's eye view, you can see that it's actually not spherical. It's got an almond shape. And that's what you would expect if you just chop off a piece of the two nuclei. And so it is, it's got an asymmetry to begin with. Now, if this matter behaves collectively, then you expect that you will build up some pressure gradients. And the pressure gradient should be larger here in the x direction than the y direction because the density is a little higher. If that indeed happens, then those the difference in the pressure gradients will build up an anisotropy in momentum space. So you should have more stuff at higher momentum in the x direction than the y direction. And that's what we can look for experimentally. And the way we do that is by looking at the opening angle distribution of all the possible pairs. And if this is completely symmetric, then the opening angle distribution should be completely flat. And if there is a translation of the initial asymmetry into an anisotropy in momentum space, then we should see that. And this is the measured opening angle distribution at a couple of different impact parameters, a couple of different momenta. And you see that, lo and behold, it is not flat. There is a definite anisotropy. So we can then subject this distribution to Fourier analysis. And the second Fourier coefficient measures the amplitude of this anisotropy, and that's related to the strength of the pressure gradients. And that second Fourier coefficient we call elliptic flow. So you can look how that depends on the impact parameter. And this is plotted here now, the second Fourier coefficient as a function of, here you have large impact parameters, just grazing collisions all the way to very central collisions. And you can see that this actually reaches 8%. Now that may sound small, but actually an anisotropy of 8% in such a fast collision is really a huge anisotropy. And that to get that, you need a very large pressure buildup. The data points are from 2 different experiments, so we know that it's right, we've cross-checked. And the red bars are what you would expect if you describe the stuff inside with hydrodynamics. You can look significantly more differentially at this magnitude of the elliptic flow. Here it's shown as a function of the transverse momentum of the particles and plotted separately for mesons, which are QQ bar pairs, and baryons, which are triplets of quarks. And you can see that there's a definite dependence. They grow with transverse momentum. And that's what you would expect, because anybody that gets a larger collective kick has to have a higher transverse momentum. The lines show the prediction of hydrodynamics, and you can reproduce the data actually quite well, assuming 2 things. The first one is that your hydrodynamic expansion starts very quickly, less than 1 Fermi over C, namely only a few times longer than it takes those nuclei to pass through one another. And the other is, if you want to get the pions and protons and antiprotons right, that system has to spend some of its time as a quark-gluon plasma. The plasma has a different equation of state, different relationship between the pressure and the energy. And so this was one of our first indications that we really were making a quark-gluon plasma in these collisions. Now, there's another little fact that you have to get right if you're going to reproduce the measured elliptic flows, and that is that the viscosity to entropy ratio has to be very tiny. And that's what led us to realize that the quark-gluon plasma flows like a nearly perfect liquid. Now, I've been talking a lot about the second harmonic. People here who do cosmology were probably thinking, there's hundreds of harmonics. Indeed, higher harmonics exist in collisions of nuclei also. That's easy to understand why that should be true, because we know that the nucleons inside nuclei move around. They're not fixed, they're not static, and so the locations of the actual nucleon-nucleon collisions fluctuate, and you do get some of the odd harmonics, such as V3, which we call triangular flow. And the higher the harmonic, the more sensitive it is to the viscosity to entropy ratio. And that's kind of easy to understand, because you know that viscosity increases dissipation. So if the system is going to remember that fluctuating, slightly triangular shape, that information has to be very effectively translated from the initial state to the final state. So we do the rest of the Fourier analysis. And what you see here is the transverse momentum dependence of the second, third, fourth, and fifth harmonic. This is at RHIC. This is at the LHC. And you can do the same thing for your hydrodynamics calculations, and you can fix what the entropy, the viscosity to entropy ratio is to reproduce the data. And please note that here you have 0.12 for RHIC, which is lower temperature, has a lower energy by a factor of 10 than the LHC. And here it is 0.2. So this already gives us some idea of the viscosity of the quark-gluon plasma. You can use these data and the uncertainties to make this band of what the entropy, the viscosity to entropy ratio of QCD matter looks like. And you see that it has a minimum at the critical temperature. Remember, I told you that's just about 150 MeV. And then it goes up on either side. And there are lots of examples of other kind of matter where that is true. So no surprise. What is maybe more surprising is just how close this is to zero, and this green line that sits just above zero, which is the quantum mechanical absolutely lower limit. This is, turns out the quark gluon plasma is one of the best flowing liquids that we've ever made. Now, this was a real surprise that the viscosity over entropy, or the viscosity per particle, if you will, is so small. In order to wrap your intuition around it, you have to think about viscosity as the inability to transport momentum and sustain a wave. So the higher the viscosity, the less of a wave your liquid can actually make. You can look at this quantitatively over here as the relationship between the viscosity, the particle density, the mean momentum of the particles, and the mean free path. So low viscosity, you put together the density and the mean free path, translates to a large interaction cross-section. And that's what transports disturbances quite well. Okay, so if you have good momentum transfer, and that means that the neighboring fluid elements talk to one another quite effectively, and that's what told us that the quark gluon plasma is strongly coupled. If you really have a dense system where the fluid elements are all talking to one another and transferring information well, then you would expect that this should be rather opaque. If you send a fast quark or a gluon through, you can think of it as colliding with clumps of gluons rather than individual quarks and gluons. So let's see if that's true. We do that by measuring high momentum particles. Here is the distribution of neutral pions out to 13 GeV. These days, we wouldn't say that's very high momentum, but we were very proud of the measurement when we first made it. The black points are the data. The red lines are the predictions from QCD. And you can see that the lines agree with the data really very well. So you make that measurement in pp, that's your baseline. Then you make the measurement in gold-gold collisions, and that's the red points. And you compare it with what you know from proton-proton collisions scaled up by the number of individual nucleon-nucleon collisions in a head-on gold-gold. And that's the blue. So your eye immediately tells you that there's a significant deficit. If you take the ratio of the red over the blue, you form a quantity that we call the nuclear modification factor, or RAA, which some of my students had fun learning about. So that ratio is plotted right here. And you can see that what we actually see, the number of neutral pions in a head-on gold-gold collision, is about 1/5 of what it should be. Of course, when we saw this, the immediate question we asked is maybe we made some kind of a mistake. And here you see the same nuclear modification factor for photons, and those are right at 1. So really, we're doing the calculation of the number of collisions correctly. You really have a high opacity to partonic matter that has color charge. Now with the LHC, one can go way past 20 GeV. We see that charged particles out to 100 GeV and actually jets out to 300 GeV continue to be very strongly suppressed in quark gluon plasma. And here is the LHC measurement of photons and also W and Z bosons, and you see those all have a ratio of 1. So you see that we have good evidence that the plasma is quite opaque. Now you can do better than that. Remember, I showed you in the cartoon, you have a large momentum transfer, so you have a pair of partons that are going off through the plasma. So if you require one with a high momentum, this here is a measurement by CMS. They have a jet at 205 GeV. So if you see one with a really high energy, it's most likely that it came from the surface. And that means that its partner that scattered off at 180 degrees had to make its way all the way through the plasma. So CMS asked, well, what happens to the partner? And here you can see that the partner just sort of oozed out with only 70 GeV rather than the 200 it probably started with. Further evidence of the opacity. It's actually quite interesting that if you turn up the mass of the quark to a charm quark, the plasma seems to be just as opaque to charm quarks as it is to light quarks. So what we would expect from strongly coupled matter. And indeed, we see that the quark-gluon plasma has a lot of similarities to other systems that are strongly coupled. All of those systems flow and exhibit very interesting phase transitions. One nice example is strongly correlated condensed matter. You see liquid crystal phases and superconducting phases in the strongly correlated systems in condensed matter. Amusingly enough, cold atoms behave a lot like hot plasma. This is a picture actually of an ultra cold atomic gas at 10 to the -7th kelvins, which has a resonance excited with a laser that's strongly coupled. And you can see that they see the same kind of flows as we saw in the quark-gluon plasma at 10 to the 12th kelvins. Again, it's the strong coupling that's common. Interestingly enough, dusty plasmas and warm, dense, normal electromagnetic plasmas also have some interesting liquid and even crystalline phases. And indeed, you can find a lot of papers that describe the rings of Saturn as a dusty crystalline plasma. And in all these cases, you actually have something you have the same kind of thing going on. There's a competition between attractive forces and either repulsive forces or the kinetic energy in the case of the quark-gluon plasma. And the result of these competitions is that you have many body interactions rather than the pairwise interactions we're used to thinking about when we think about particle scattering. And QCD is a very nice test lab for these kinds of systems because we definitely know the Lagrangian. It's not easy, but we know what it is. Okay, so how would we go about calculating transport in the quark-gluon plasma? Well, we could use the weak coupling limit, and we know how to do calculations in QCD, can use perturbation theory, set up a cascade of interactions of quarks and gluons, and that's calculable and soluble. The problem is that we have lots of evidence that the system is strongly coupled. Another way, of course, is to use lattice. We heard about all the fabulous things one can do with lattice last week. The problem is that the lattice is mostly a way to calculate the properties of a static system, and we want to calculate transport. There's some work going on to calculate transport coefficients on the lattice, but that's not very easy, so that's in its infancy. Interestingly enough, there's another way to go at this, and that is to look in the infinitely strongly coupled limit. Instead of describing this stuff as an assembly of quarks and gluons, we can describe it as a pure field. And amazingly enough, a way to do this is by using the duality between gravity and a supersymmetric four-dimensional quantum field theory, also known as ADS-CFT. Now, how does that actually work? Well, let me show you the cartoon that probably makes it easier. So if you think of our world as a four-dimensional sphere, the duality with gravity and this four-dimensional quantum field theory requires that you have a fifth dimension with a black hole in the middle. And you have ripples along this fifth dimension from our world on the surface. And those ripples are actually the interactions between quarks and gluons and the strongly coupled quark-gluon plasma. Now, I found it pretty exciting that string theorists started to think about quark-gluon plasma. And they've actually done some interesting calculations that actually look like the data, which is even more wonderful. Now, the way to think about this is, so here's our four-dimensional world sheet, 3 spatial dimensions and time. Here are a couple of quarks. And the string that connects them is what hangs down into the fifth dimension. So the closer they get to the black hole, the stronger their interaction with the quark-gluon plasma. And my friends tell me that if you set this up as a gravity problem, it's easy to solve. I'm not completely convinced it's that easy, but maybe for theorists, it's pretty easy. So I've kind of set up a dichotomy, and indeed, there is a really raging debate going on in our field of what exactly is inside a hot, dense QCD plasma. Is it individual gluons? Is it pure fields? The one would be the perturbative picture. The other one would be the ADS-CFT picture. My intuition says neither of those is probably right. Perhaps what you really have are multi-gluons, some composite quasi-particles that are constantly splitting and reforming. Sounds crazy, but in fact, in the theory of classical liquids, voids form these sorts of quasi-particles. So that may be the right picture. One way to try and get at that is to look at the mechanism of this large energy loss that we have experimental evidence for. Is it radiative, namely your quark or gluon going through the plasma radiates gluons, just the QCD analogy to normal Bremsstrahlung? Is there elastic scattering among the quarks and gluons going through with the stuff in the plasma? Or perhaps alternatively, as your quark is going through and dragging its little string down towards the plasma, the energy loss is by exciting collective modes in the quark-gluon plasma. That would be the ADS-CFT answer. In order to answer this, what we need to do is to measure dynamical properties of this QCD matter. Things like the viscosity, which I showed you. We could measure the speed of sound, the diffusion, namely the transport of momentum energy and particles through the plasma. So one question you might ask is, does the dense plasma increase the frequency and angular range of gluon splitting? As a parton goes through vacuum, it starts to radiate gluons, and those then flip into quark-antiquark pairs, and that's how you get an assemblage of hadrons at the end that we reconstruct experimentally as a jet. So what actually happens if you then bury this inside a quark-gluon plasma and you start to split these particles into gluons that are similar in scale to the gluons inside the plasma? Then you would expect the jet to be broadened, gets kicks each time there's an interaction with a plasma gluon, and you actually have a much broader cascade of gluons emitted. High energy jets fragment mostly outside the plasma, and so they perhaps interact as a coherent object on their way through. As we know, they still lose energy, but not quite as much. Now, I like this picture because that's something we can go after experimentally. So one of the key quests right now is to search for the lost energy. We know there's a lot of it, 100 GeV oftentimes. Where does it go? Well, if the ADS-CFT picture is right, you don't produce any gluons. You just excite collective modes in the plasma, perhaps plasmons or some kind of motions, collective motions. Alternatively, if you have the plasma enhancing gluon radiation and changing the way the gluons split, then you should maybe see that when you reconstruct your jet. So if you just have extra gluons at small angles, so enhanced radiation but in the same way as it happens in vacuum, then what you should see is extra gluons at small angles that are inside the jet cone. Alternatively, if the radiated gluons completely thermalize in the quark-gluon plasma, then they should be simply gone. And if you look around your high PT pi 0, the jet should look sort of like a normal jet, just less of them. Alternatively, if that nice, enhanced branching picture is right, then the jets should have extra particles that are still correlated with the jet, but broaden the angular distribution. So we've gone off and looked for that. I won't subject you to going through all of the data plots, just put these here so that you see there are a lot of different measurements. The summary, though, is that this is, if you look at a jet in vacuum, like in proton-proton collisions, you see a particular distribution of particles carrying a large fraction of the jet's momentum, medium, and very small. If you look at the LHC at these 100, 200 GeV jets, you find out that they actually look pretty normal. There's no suppression of the high PT particles. There's a small enhancement of the low PT particles. So they look almost normal jets, just fewer of them. But you see a significant extra number of particles at very large angles. Conversely, if you look at RHIC, where the jets are much lower energy and so very well matched to the plasma itself, then you see a large suppression of high PT particles and a large enhancement of the low PT particles. So the jets really broadened and softened, as well as there being fewer of them. So in order to sort out how do we get from broadened jets to normal looking jets as you go from 10 GeV to 200 GeV, what we need to do is make the same measurements at both RHIC and the Large Hadron Collider. And why do you want to do that? Well, you know the temperature is different in the two cases, but you'd like to make the probe the same. So in order to do that, we need to add a full jet reconstruction at RHIC using both electromagnetic and hadronic calorimetry. That's to repeat the measurements of the rather normal looking jets at high energy at the LHC. And we need to look at photon hadron and jet hadron correlations, namely both of the scattered guys at the LHC. And we can do that using the ALICE detector. And I just would note that this is data that are going to start being taken in a couple of weeks. So it's a nice thesis opportunity if anybody in the audience is looking for a thesis. Before I finish, I want to talk about another mystery. So I mentioned that the equilibration has to be very fast. You have to start your hydrodynamics very soon after the nuclei cross one another. If you wait too long, or you build up the pressure too slowly, then you don't get a large enough elliptic flow, that second Fourier coefficient. We see that hydrodynamics works, but that implies a local equilibrium, or at least a local equipartition of the momenta of all of the particles inside the plasma. And we do know that with normal known cross sections, just collisions, independent collisions of quarks and gluons can't do that fast enough. So, how do you actually equilibrate so quickly? There are papers you can find that, yes, of course, you get a fast equilibration because you actually make a tiny black hole. I don't know, maybe. I find that kind of surprising. There are calculations that you could almost get there fast enough through plasma instabilities. Or maybe the gluon distribution starts from something that's already close to thermal. We actually found a real surprise in the last couple of years that maybe argues towards the last explanation, and that is already in proton or deuterons on gold or on lead, we see a flow pattern very similar that's characteristic of the quark-gluon plasma in heavy ion collisions. Shown here is the ratio of the elliptic flow, the V2 divided by the ellipticity, so the asymmetry of the system coming in, as a function of the number of particles in the system. Here's all the heavy ion data, and this stuff down here is protons or deuterons on ions. And you can see they really follow a remarkably good line. A few years ago, nobody thought that it would be possible to actually form a teeny tiny droplet of plasma. You always think of plasma as having a relatively large size compared to the interparticle distance. Here it's not so large, but it seems to behave just like a plasma. So this again says it would be very important to find out what is the gluon structure that the system equilibrates from. So how are we going to do that? Well, I would put it to you that since hot dense gluonic matter is pretty weird, maybe cold dense gluonic matter is weirder than we thought. So you can look deep inside a nucleus. What happens is as you look deeper and deeper inside, you're looking at gluons that carry a smaller and smaller fraction of the nucleon's momentum. And there's more and more of them because remember, the number of gluons is not conserved, and the interactions actually cause there to be more and more gluons. So at high enough density, it may very well be that the processes that split one gluon into two are exactly balanced by combination processes where two gluons fuse into one, causing the density of gluons to actually be saturated. And there are some very clever calculations of this that predict the conditions under which this could happen. To check that experimentally, you need to increase your probe energy, namely to have a higher and higher resolution of the distribution of gluons inside. And you need to increase the energy also to reach smaller and smaller momentum fraction. There's some evidence from RHIC data already that we may in fact be seeing some saturation of the gluons. I think in the interest of time, I won't talk about it in any detail. Intriguing evidence, we're not absolutely certain yet, but I would point out that in a proton on a nucleus or a deuteron on a nucleus, the dynamics of the incoming parton, so of the probe, is still pretty confusing. Because if you look at this picture here, here's a proton about to hit a nucleus, and before you have the hard scattering that resolves the number of gluons, your quark inside the nucleus or gluon inside the proton coming in can lose some energy in the nucleus. It can multiple scatter. So it's hard to get quantitative. So what do we do about this? Well, I propose what we should do about this is change the probe. So in our collision so far, where we probe a nucleus with a proton or a deuteron, our probe, our gluon probe, it's a gluon that's exchanged, that has a structure that's almost as complex as the nucleus itself that we're trying to figure out. As I mentioned, you can have scattering and energy loss before and after your hard scattering. And so when you measure the distribution of stuff coming out, you've somehow mixed together the dynamics of the probe itself with the structure of the nucleus you're trying to measure. However, if you change to an electron beam, then you use the process known as deep inelastic scattering. You exchange a virtual photon. That's a point-like probe. And furthermore, it's not going to interact with your nucleus in lots of small ways before the large momentum transfer. And furthermore, you can control the kinematics. You know what the energy of the transferred photon is if you can measure the electron that's scattered off. So if we can do this, then we can actually ask some really basic questions like, what is the gluon density very deep inside a nucleus? And you can be more differential and ask, what's the distribution of gluons inside? And does it really look like individual nucleons piled up on one another? Or is it something that looks more collective and closer to thermal distribution to begin with? Given what I showed you from proton nucleus collisions that look like you actually expand like a little quark gluon plasma droplet, a really interesting question is, does the photon heat a little spot in the nucleus high enough to make a plasma? There's a lot of debate about that recently at a big conference that a number of us went to. And about half the people said, oh yes, and the other half said, no way. So this is a really great experimental question. So how to do that? Well, there are plans to build an electron-ion collider. A few weeks ago, the long-range plan for nuclear physics was just released, and that's the next plan for QCD in the country, is to build an electron-ion collider. You say, well, gee, how are you going to do that? Well, there's two options. You can add electrons to the ions at the relativistic heavy ion collider, or you can add ions to the electrons at Jefferson Lab. We don't know which will be the way to go. Those studies in R&D are just starting now. There are some concepts for what a detector might look like. I think it's time now for us to hone what the questions are we want to answer, and then we can take these kind of PowerPoint designs to something more serious and know that we can make the right measurements once the collider is built. So I think with that, I'll conclude. I hope I showed you that hot QCD matter is a nearly perfect liquid. It has an almost frictionless flow. This liquid is very highly opaque to quarks and gluons. We're not really quite sure why that is so, because we don't really understand the mechanism of transport in the quark-gluon plasma. Upcoming measurements will tell us a lot, so that's exciting. We also know that the thermalization is very fast, but we don't know how that proceeds. And we also don't really know how it's possible to make such tiny droplets of plasma. And there's still debates. We're not even sure that these little flow patterns we see in proton-nucleus collisions are droplets of plasma. So there's a lot of stuff to be figured out yet. And hopefully I've convinced you that the physics is indeed very cool. Now, maybe we start off with a gluon system that's at or approaching an equilibrium distribution. That would make it a lot easier to start up your hydrodynamics, which requires a near equipartition. We're trying to get at that using proton-nucleus collisions, but there's a hard job for experiment and theory to disentangle the dynamics of the probe from the structure of the matter. And I think the next step is to probe that structure directly with electrons at an EIC and see how do nuclei actually emerge from cold, dense QCD matter. Thank you. Clear as mud.
How well is known where this base boundary is?
So last week, Zoltan Fodor told us, well, we actually know the critical temperature reasonably well from lattice. Experimentally, there's a lot of work to be done. Actually, let me show you, go back to the phase diagram here. We will know the answer to that experimentally reasonably soon. So this yellow spot is supposed to be the critical temperature. And somewhere around here, it should be a crossover, and here a first order phase transition. And there is a beam energy scan program at RHIC to try and really go through this in small steps. There are some first results that are fairly promising, that on the, either side of this, we seem to see some differences in the way the fluctuations work, in particular fluctuations of net protons. However, the error bars are still pretty big, so I'm not going to try and convince you that we know the answer yet. But there's going to be another campaign with RHIC to do that with much better statistics. So I think we should have an answer to that in the time scale by surely by 2020, probably sooner. Well, there were electrons on protons at Hera, but electrons on heavy ions has never been done. The other thing that I really didn't talk about at all, that's another big driver for the electron-ion collider, is to polarize the electrons and the protons. Because one of the big mysteries, you'd think, yeah, we know that the proton has a spin of a half, and we know it has 3 valence quarks, each of which has spin of a half, so they're like this and then one odd one, right? Wrong. Turns out that the quarks, the valence quarks, carry about a quarter of the proton spin. So then we thought, okay, it must be in the gluons. So we put polarized protons into RHIC, and it took a lot of work to find any evidence of the gluons carrying some of the spin of the proton. Now we have some evidence that they do, but it's not clear that it adds up yet. And so where else can it be? Well, in the orbital motion of the quarks and gluons inside the nucleon, and that's something else we're going to actually quantify with the electron-ion collider by polarizing the electron and the proton. And that's not been done like that before.
Barbara, I have a question about this rapid thermalization. So in a strongly coupled system, I would guess that they thermalize it basically in one fermi.
Yeah, actually, right.
One is sort of order of magnitude. So is you're surprised that it's not like one, but it's like a half or a quarter? Or
well, so the reason the surprise, if you want to get the hydro to reproduce the flows quantitatively, you have to thermalize in like 0.6. But if you just calculate a cascade of quark and gluon interactions, your thermalization time is several Fermi over C. So it's really the mechanism of why you can thermalize so quickly. That's the surprise. It's not, if you do have quark and gluon interactions, you have to boost up the cross section somehow, which maybe strong coupling does. But so far it's, you know, let's treat it as a parameter rather than really understand the underlying science. So that's where the surprise comes from. It's the cross sections.
So are the time scales for decisions about things like EIC dependent on people making theoretical predictions about what things think?
Good question. It's actually both. The expected plan, which is sort of driven by hope, reality of what you can do on what time scale, and funding in the field, says that we really need to make the science case on the time scale of 2017, 2018. And that requires both theoretical work and also some serious design work on the experiment to convince ourselves and you that the quantities are measurable with enough precision to answer the scientific questions. Then the next step really is to refine the designs between both, at both Brookhaven and Jefferson Lab. The technologies are different. The cost estimates at the moment are different. The technical risk is different. As you can guess, the cost and technical risk are anti-correlated. And we do need some more work to really determine what the right root S is, because the current designs have different collision energies. So we've got probably 5 years of work to go before a down select can be made.